This last part is going to focus on the quantum mechanical model, the current model that we have used to describe what is happening inside the atom. Hopefully it's going to help you see why I wanted you to watch that video that we started with, just kind of reviewing the basis of electron configurations, because I think your knowledge of that will really help you with what we're going to be talking about right now. So as we've talked about previously, Bohr's model showed that it worked really well for hydrogen in terms of the circular orbits, but the quantum mechanical model allowed for a more wave-like nature to the movement of the electrons, which you see in the picture to the right. Hopefully this is a little bit of review. Heisenberg, Schrödinger, and de Broglie all contributed in various ways to that quantum mechanical model. Heisenberg's had to do with both the position and the momentum. De Broglie we've already talked about how waves can have masses and the particles can have wave-like properties. And then Schrödinger's is the one we're going to be focusing on. It's the basis of electron configurations, and that is describing the address of electrons as they go through the standing wave process in the atom, called quantum numbers. So how we came up with this idea of quantum numbers is in part because of the structure of the atom in terms of the orbitals. The physicists that we just talked about kind of worked together to develop this idea of wave function, that your electrons can have properties of waves, and you can kind of see that in the pictures below. I'm showing you three particular orbitals, 1s, 2s, and 3s, and you can see kind of the wave-like function that is being shown as electrons are moving around those orbitals. But there are specific energies associated with those wave functions. We will only find electrons in those locations that have a certain amount of energy associated with them, and that the general region in which we find those electrons at is basically a probability region. This is all mathematical, and that 90% of the time we are likely to find an electron in those generalized regions known as orbitals. And you can kind of see that with the orbits, and again, going back to Heisenberg, but how you cannot describe both the position and the momentum at the same time. You can do one pretty accurately, but you can't do both. So quantum numbers is, again, trying to describe the general address for the electrons within the orbitals. We've talked about each of these in terms of electron configurations, and I'm going to go through each of these in depth. We'll talk about the principal, the angular momentum, the magnetic, and the electron spin. And the picture above is just kind of representing each of them. And again, we'll see them a little bit more on the next few slides. So the principal quantum number is basically associated with a row on the periodic table. It refers to the general space for that orbital. They tend to get larger as we get to higher n values, and they tend to have more energy. You don't have to write this down in your notes, but they are sometimes called shells. We also talked about them as energy levels. And they start with an n of 1, corresponding to the first row on the periodic table, and so far go up to 7. In theory, they could add on if we added on more and more rows of electrons, or sorry, more and more rows of elements on the periodic table. So every electron has its own principal quantum number. Some of them obviously can have the same, but they also have an angular momentum quantum number, which kind of helps to narrow down the area in which we're likely to find those electrons at in those general energy levels. It depicts the shape of the orbital. S is more spherical, P is kind of dumbbells. I always refer to D more like four-leaf clovers, and then we have the hula hoop one at the end. And then the F, which is the very last picture, is kind of double four-leaf clovers. Each of those general areas that depicts the shape of the orbital has its own angular momentum quantum number. So if you are in the S sublevel, that's another way we described it before, you would have an L of 0. Your L's are always starting at 0, and they go up to n minus 1. So if you're in the second energy level, you can have an L of 0, and you can have an L of 1, because you have a 2s area of electrons, and you have a 2p area of electrons. When you are in the third energy level, your n is 3, so you can have an L of 0, an L of 1, and an L of 2. You're adding on the 3d sublevel. And then finally, if you have an n of 4, you can have L's of 0, 1, 2, and 3, because you can have 4s, 4p, 4d, and 4f as places in which your electrons can go. This would continue to go on, so if you got up to period 6, in theory you could have an L of 0, an L of 1, 2, 3, 4, and 5, so up to 6 different areas in which your electrons would be located. The magnetic quantum number is referring to the location, which orbital of the different ones that we just saw are you likely to find your electrons in. The S sublevel only has one orbital, so if you are in an L of 0, you have to have an ML that falls between negative L and plus L, and the only number that would fall between that would be 0. But if you're in the P sublevel, because there's 3 potential orbitals in that P sublevel, you can have L's ranging from negative 1 to plus 1 with 0 in the middle, and you can kind of see that in the picture below. With the L of 2, when you're in the D sublevel, you can have L's from negative 2 up to plus 2, which gives you your 5 orbitals. And then finally, if you're in an F sublevel, an L of 3, you can have MLs ranging from negative 3 to plus 3. Final one's a little more straightforward, and it's this one that allows every electron to have its own unique set of quantum numbers within an atom's orbitals, and that is the MS, the electron spin quantum number. Electrons are negatively charged, and they each want to go towards a magnetic field in one of 2 orientations, either clockwise or counterclockwise. And so because they're both present and they're both repelling one another, it makes sense to have one going in a clockwise direction and the other one to go in a counterclockwise direction. And we represent that as plus 1/2 and minus 1/2. It does not matter which one you put as plus 1/2 and minus 1/2, but in a given orbital, you cannot have 2 with the same designation. A couple other terms I just want to make you familiar with. If you have unpaired electrons, once you place all your electrons in your orbitals, you have an electron that's not paired with another. They are paramagnetic. They are drawn towards a magnetic field. But if they have no unpaired electrons, they are considered to be diamagnetic. That means they either have completely filled orbitals or they have completely unfilled orbitals. So I'm going to show you a couple of examples with 2 elements. We're going to look at all of beryllium's electrons, and we're going to look at sulfur's valence electrons. Beryllium, if we were going to write its electron configuration, it has 4 electrons, the first 2 going in 1s, the second 2 going in 2s. So if I was going to find a home for those 4 electrons, I always start with my lowest n possible first, which would be 1, and I would have 1 in the n. Because S has an L of 0, that would go next. The ML goes from negative L to plus L, so it too would be 0, and I just designated MS as plus 1/2. The next electron would also go into 1s, and it would look exactly the same because it's all in the 1s sublevel with that 1 orbital, but it would have a negative 1/2 designation for its magnetic spin. The 2s electrons are going to look very similar to the 1s electrons, except that their n will have changed because they're now in that principal energy level of 2. They still are in the s sublevel, so they have an L of 0, and they only have 1 potential orbital, so their ML is 0. 1 has to be plus 1/2, 1 has to be minus 1/2. The last one we're going to look at is sulfur. Sulfur actually has 16 electrons, and we're going to focus on the valence electrons. So we're going to look at the 3 s's and the 3 p's. So when we start with the 3 s's, our n would be 3 to represent those 3s electrons. We've already seen with s how the L is always 0, the ML is always 0, and the spin would be plus 1/2 or minus 1/2. It's the 3 p's that are going to be a little bit different. We would still have an n of 3, but we have moved from an L of 0 to an L of 1. Remember that if you're in the 3rd energy level, you can have 3 different L's, 0 for S, 1 for P, and 2 for D. Your ML ranges from negative L to plus L, and we always fill up our electrons 1 in each orbital before we add in a second. So I start with negative 1 and just go from the left side to the right. And I put 1 in each of the orbitals first. So I'm going to do that first 3p electron, then I'm going to do my second one, and I'm going to do my third one. Notice that the n is the same because they're all 3. The L is the same because they're all 3p. The ML is different because I'm placing 1 electron in each of the orbitals, so each orbital has its own ML value. -1, 0, and +1. And just so I could keep it straight in my mind, I just had them all spinning in the clockwise direction to get started. I do have a fourth electron, and so I can pick any of those 3 ml values to put the fourth electron in. I just go back to the beginning and notice that the only difference between my first electron and my second one is that the spin is now -1/2. So what we're going to do right now is see how much you've gotten out of this different language I've talked. And we're going to look at these 6 orbital designations and determine which are accurate and which are not. So the first one we're going to look at is 1s. 1s tells us we have an n of 1 and that we have an L of 0. And that makes sense. You can have an L that starts at 0 and your n has to be anything above 0. You cannot have an L equal to your n. So we can only have one sublevel in which electrons are placed in the first energy level, and that would be 0. 1p would represent an n of 1, and our L would also be 1, and that is a problem because you cannot have n equal L. L can be up to n minus 1, and 1 minus 1 would be 0, so that one is not possible, which is why you never see anything with an 1p designation. We're next going to look at 7d. 7d would give us an n of 7 and a L of 2, I believe. Any L would be fine up to and including 6. SPD 0, 1, 2. I think I made a boo-boo there. I think that one should be an L of 2. And so that one is correct. I'll make sure I go back and fix that. Sorry about that. L of 3 would be 7F. 9S, you would have an n of 9. Again, all s's start with an L of 0, and you can go all the way up to 1 minus that n value, so n minus 1, which would be 8. So this would be fine. We have a 4f. 4f would give you an n of 4 and an L of 3. That is 1 minus, 3 is 1 minus 4, so that would be totally fine. And then we have 2d. 2d would give us an n of 2, and it would give us an L of 2. And again, you cannot have an n and an L equally one another, so that would not be a correct designation. You can only have an 2s, an n of 2, L of 0, a 2p, an n of 2, an L of 1. But you cannot have a 2d. And then this is the last example we're going to take a look at. It says, which of the following sets of quantum numbers are not allowed? And then say what's wrong if they aren't allowed. So I've given you 3 potential quantum numbers. You'll have ones on your homework that are just n and L. You could have n, L, and ml. You could have n, L, and ms. You could have n, ml, and ms. And just tell me how many possible electrons could have that designation. So n of 4 would give me the 4th energy level, and L of 3 would give me a d, so 4d is possible. ml, however, has to range from -L to +L, and 4 of ml is way higher than 3, so this one is not possible. It's not allowed. N and L are great, but ml needs to be -3, -2, -1, 0, +1, +2, or +3. It has to represent one of those 7 F orbitals that we would expect to find. And then our second example, n of 0, L of 0, ml of 0. The problem with this one's from the beginning. Your n has to start with 1 and go up as an integer. L has to be n minus 1, and 0 minus 0 isn't possible to, it doesn't give you anything new. ml would be fine for an L of 0, but again, you can't have an n of 0. And so that's why we have a problem. Again, I will definitely go over this a little bit more in class, and I have another little flow chart to help you with this. Again, I just would try to relate this as much as you can to the electron configurations that you've done previously. I think that'll help you a lot.